Okay, welcome back. Here's part 2 of our Chapter 5 overview. We just finished looking at an example of a binomial probability distribution and figuring out the probability of getting 6 wins out of 10 attempts at betting red on a roulette wheel. Let's see. One more example. And here's a normal probability distribution. Heights of U.S. women follow N 64.3. This notation is new. The capital N means it's a normal distribution, and then you have to specify for a normal distribution the mean and standard deviation. So U.S. women have an average height of about 5'4", 64 inches, with a standard deviation of 3 inches. Okay. What is the probability that a randomly chosen woman will be 5'2" to the nearest inch? So in reading this, you have to think, okay, we're talking about a random variable here. The random process is select a woman at random and measure her. And then the random variable is her height. And what is the probability that it'll turn out to be 5'2" to the nearest inch? Okay, so I would draw a picture. I would draw a bell-shaped curve with 64 inches in the center, and then I would shade an area that was above 61.5 and 62.5, because it's that range of values that describes, what heights a woman would have to be 5'2" to the nearest inch. Okay, so you're going to find that shaded area with normal CDF. The syntax is lower end point, upper end point, or lower bound and upper bound of the area. And then you have to tell the calculator what's the mean of the distribution, what's the standard deviation of the distribution. Hit enter, and you get about 10.6%. So about 10.6% of all women are 5'2" within half an inch to the nearest inch. What percent of U.S. women are shorter than 5 feet? My wife is 5 feet tall. So that would be a normal curve. Again, if I had a blackboard, I'd draw this. Picture a bell-shaped curve, put 64 inches in the middle of the distribution, locate 5 feet, which is 60 inches, considerably to the, on the lower end, in the left-hand tail of the distribution, and then shade an area under the density curve to the left of 5 feet. It'll be an entire tail. And in theory, you're talking about what's the probability that that random variable will be someplace between negative infinity and 5 feet tall, negative infinity and 60 inches, in a distribution with a mean of 64 and a standard deviation of 3. Well, there gets to be a problem here of how do you enter negative infinity. And the convention that I'll suggest you use is to recognize that essentially no observations are going to be more than 10 standard deviations away from the mean. So you take the mean, 64, and you take 10 standard deviations, multiply 3 times 10 to get 30, and do 64 minus 30, 10 standard deviations below the mean, mu minus 10 sigma, to get 34. 64 minus 30 is 34. And this is essentially saying, okay, realistically, no women are going to be shorter than 10 standard deviations below the mean. That's somewhat under 3 feet tall, right? So instead of saying negative infinity to 60, just ask the calculator, what's the probability that you're going to be between 34 inches and 60 inches? You can even, if the mean and standard deviation are clunkier numbers, you can round. If the standard deviation is 2.7, round to 3 and then use this rule. Or in the calculator, enter right into this space, just enter whatever the mean is minus 10 times whatever the standard deviation is. The calculator will crunch the numbers for you. Comma 60, comma 64, comma 3, and the calculator says about 9.1% of women are as shorter than my wife is. Okay, well that's it for the overview. I think I would recommend that the next thing you do is to get into the activity, and that will focus on normal distributions and working with your calculator. And I did a couple of videos that show some examples and work some of that activity with you. I think it'll be a kind of a tough activity to do completely on your own, but I think with the help of that video you'll manage. And then as you get into the homework after the activity, you might want to open up this document that's also on Moodle, or I may have included it in your handout packet, called Choosing a Probability Model. Because as I referenced in the earlier video, the hardest part about these problems really is figuring out which model to work with. So let me talk through this with you just briefly right now, briefly meaning maybe 5 minutes. In this document it gives you 4 examples. Okay, 4% of Acme light bulbs are defective. What's the probability that a 24 bulb carton will contain no defects? Acorns weigh a mean of 15.9 grams with a standard deviation of 1.6 grams. What percent of acorns will weigh between 16 and 18 grams? The Canyon Diablo meteor struck 50,000 years ago in what is now Arizona. What's the probability that it struck between noon and 2:30 p.m.? And finally, in Springfield, 15.2 cars are stolen per week on average. What are the chances that exactly 16, or part B of the question, what's the probability that fewer than 10 cars will be stolen in the next week? Okay, so here's how I would go about choosing a model, and this is very much what you should be doing when you're doing those early matching questions too. It says, here's a scenario, what's the probability model? I would start out by thinking, is it discrete or is it continuous? Can you tell, think about what the random variable is in the situation and whether it's discrete or continuous. So for number 1, let's see, 4% of Acme light bulbs are defective. What's the probability that a 24 bulb carton will contain no defects? Okay, so what's the random process here? I think the random process is you've got a 24 bulb carton of 24 bulbs in a carton, and you draw one of them out and you test it to see if it's a defective bulb or not. Okay, if this is, I guess, a dichotomous random variable, because oh no, I take it back. I guess what we're interested in is how many defects are going to be in the carton. It's not a dichotomous random variable because the random process is not just testing one bulb. What it is it's testing all of the bulbs, all 24 bulbs in the container to see how many defects there are. And that random variable could have an outcome of 0, no defects, or 1 defective bulb, or 2 or 3 or 4, or any number up to 24, right? Aha, it's a discrete random variable. 1 through 24, I can't have 1.5 defects, so I'm over here in discrete, okay? And I would do that for each of these guys. And then within discrete, once I'm in discrete, I think about my models. I've got a uniform discrete where each value is equally likely. Is it equally likely? If 4% of the bulbs are defective, is it equally likely that this carton is going to have 7 defects or 24 defects or 15 defects? I don't think so. Binomial would be a random variable that counts the number of successes in a fixed number of trials. Aha. Here we've got 24 bulbs. Every time we've got a 4% chance that it's going to be a defect. So I think this is a binomial situation because I'm thinking about a fixed number of trials. Each of the trials is a Bernoulli trial, meaning it's got just a dichotomous outcome. It's either successful or failure. And this is kind of weird, but I think in this case, I think we'd consider getting a defective bulb as a success, right? Sometimes success isn't necessarily a good thing in these problems. So what we have is 24 trials. The probability of success in every case is 4% of getting a defective light bulb. So this is an example of a binomial distribution, okay? And I'd kind of go through that process with each of these. And in this process, if you think through it, I've kind of explained why I think among the discrete random variables, the number of defects in a carton of bulbs is a binomial, and the number of stolen cars is a Poisson distribution. Poisson distributions are characterized by a random variable that's going to be a discrete random variable, just give you whole numbers, but you're counting things that are randomly scattered in space or in time, and you want to know the probability of observing a certain number of them in a fixed period of time or a fixed space interval. The cars being stolen in Springfield, 15.2 per week on average, but they're scattered randomly in time, right? And then we're asking about the probability, what are the chances of observing exactly 16 in a week, or fewer than 10 in a week. Classic Poisson situation. Okay, and then I also argue that the meteors strike, since with the information we have that it fell 50,000 years ago, we have no idea. You know, it wouldn't be any more likely to fall in any 1 hour or another hour. So basically each interval of values, each hour, each minute, each second would be equally likely as any other. So this would just be a kind of a flat probability density curve, just a rectangular space. And basically the probability that it's going to fall between noon and 2:30 is just that 2.5 hour period divided by a 24-hour period. That's how I got the 10.4% for an answer on that one. On the other hand, the weights of acorns, if you think about weights of acorns, that's a continuous random variable because it can, you know, an acorn could be 17.32 grams. But it's not uniformly distributed. You would expect the weights of acorns to tend toward one particular center, one particular average, and have most of them clump close to that average. On the other hand, like a lot of naturally occurring random variables, you'd expect there to be about the same number that were heavier or lighter than the mean, and you'd expect the scattering, the spread around the center, to be symmetric, so that, you know, the number of acorns that weigh 3 grams more than the mean would be about the same number as that weigh 3 grams less than the mean. Very characteristic of a normal probability model. And then down here I give the examples of how you'd actually calculate them. But I think the main point is, how do you find the right spot in this chart, you know? So once you figure out that it's binomial, it's not too tough to say that the probability of getting 0 out of 24 bulbs in the carton being defective is binomial probability distribution function NPK. Number of trials is 24 bulbs in the carton. Probability of success each time is 4% of the time I get a defect, and I want to know the probability of getting exactly 0. 37.5% of the time that would happen. Acorns. We figure out that this is a normal distribution with a center of 15.9 and a standard deviation of 1.6. Okay, so we go to normal CDF. For a continuous probability distribution, we don't want PDF, we want cumulative distribution. Because anytime you're calculating values in a range, you need cumulative. So for a continuous one, we're going to do CDF, normal CDF, and we're going to give it the minimum and the maximum. What's the probability being between 16 and 18, and then specify the distribution. This is the mean, this is the sigma, and we get about 38% of the acorns fall between 16 and 18 grams. Probability that the meteor struck between noon and 2:30. Uniform continuous distribution, so it's just 2.5 hours divided by a 24-hour period. Or you could see that if you drew a picture of the uniform density curve, just a horizontal line with area underneath it, you could calculate this as an area, about 10.4%. And finally, in number 4 there was a two-part question. Probability that 16 cars will be stolen. Okay, well this is Poisson PDF. Like the binomial, I want to use PDF to find an individual probability. So if you want to know the probability of getting 16 cars, you say Poisson PDF, tell it what the mean of the distribution is, 15.2, ask it the specific value you're interested in, 16, and you get that happens 9.7% of the time. But how about this one about fewer than 10? One way to do this would be you could use Poisson PDF to find the probability of getting 0 cars stolen, 1 car stolen, 2 cars stolen, 3, 4, 5, 6, 7, 8, 9 cars stolen, and add them all together. That would work fine. But much faster is in this case to use Poisson CDF, cumulative, saying find me a range of values. And what this will do is you give it the same distribution, mean of 15.2, but you say 9, and the calculator will understand that this means what's the probability in this distribution that I get 9 or 8 or 7 or 6 all the way down to 0, and it returns 6.4%. Have fun, guys.